Alrighty, so we'll get started here. Again, if there's questions along the way, you can send them in the chat. You can send them via email either now or send them later in the future if you have questions about all this stuff at another time. You can also send them to me through Edsby. So we're going to talk about trigonometric ratios. And they're relatively simple in terms of calculation. The biggest thing is just making sure that you understand what's up on the screen here right now. The triangle is always going to be right when we're working with the trigonometric ratios. Later we'll look at the sine law. In another video we'll look at the sine law and cosine law. Well, they use the word sine and cosine like the trig ratios do. They're not ratios. They are based on the ratios, but they're actually for non-right triangles. So when we're talking about sine, cosine, and tangent, the trig ratios, we're always looking at a right angle triangle. And the triangle labeling becomes very important. So the hypotenuse is, as it always has been, right across from the right angle. It's opposite of the right angle. The other two, adjacent and opposite, those sides change based on which angle we're considering. So in the case here, what we have is an angle up theta up here, and theta is just a placeholder, Greek letter for that we use as a placeholder for angles. Sometimes you'll see alpha, beta in there as well. Adjacent side is the side that is touching the angle. So it's touching the angle here, and then the opposite side is the one that does not touch the angle. And that becomes important, understanding that concept of opposite, when we look at the sine law and cosine law and determining those. So the angle is opposite from the opposite here. Okay, it's the opposite side, and then our adjacent side. If we move that angle down here, so we'll do that in red, if we move the angle down here instead of using that angle, if we're using that angle, then the opposite side now becomes here. So this now becomes the opposite side. This would become the adjacent side. So they're relative to where that angle is located. The opposite side, again, is across from the angle the adjacent side touches. And then just knowing your formula. So looking at the information given, you pick whether you're using sine, cosine, or tangent based on whether you're dealing with the two sides you're dealing with, opposite and hypotenuse, adjacent and hypotenuse, or opposite and adjacent. And a good easy way to remember these formulas is the little acronym SOHCAHTOA. Now, you're welcome to use your calculator. There's descriptions of how to do it in the textbook, and I did a quick little once over on it in some of the lesson videos, but I really recommend referring to the trig table sheet. A lot of calculators, especially if you're using computer-based stuff, they tend to go right to radian mode instead of degree mode, and thus they'll give you some wrong answers in the case that of working with this, because we're used to a degree measure, and so we don't cover radian I don't think until grade 12 anymore now. But this table here will give you the right ratio and angle matchups. So I highly recommend using the trig table to do your calculations. So we'll do a few of the examples. We're going to cover, go over some of the questions we'll do fully. Some of them we'll just discuss the setup for them. So we're going to start with the tangent ratio, and I mean the textbooks break them up into sine and cosine in one section and tangent in the other, and it's very common to see, but they're done the same. The calculations are the same. It's just a matter of which sides you're using, so I don't really see a good purpose to breaking them up, other than you often see the tangent ratio used a little more frequently in there's a few more real-world type situations you can use a tangent ratio in. But beyond that, I don't really see a good significance to breaking them up. So we'll go through everything together here. So starting with some of those tangent ratio questions, there was number 5. We'll just do an example of finding a side, finding an angle in a triangle. So in 5, we're being asked here to find the measure of both acute angles in each triangle. So both of these angles here, A and C, acute just means less than 90. So we want to find A and C to the nearest degree. And so we're given this triangle as a setup. And so we got to pick which angle we want to work with. I'm going to draw a little diagram of that in my notes here. So we got a triangle 11 millimeters and 8 millimeters, and then it was A, B, C, like that. And so now given that triangle, and I'll zoom in a bit here so you can see it a little better. With that triangle, then we have to pick an angle that we want to solve for. So if we want to solve for angle A first, then this is our working angle. Thus, the 8 millimeters is opposite, and the 11 would be adjacent. And so now what we can do is use the formula that uses opposite and adjacent, which is tan. Okay, the tan ratio there is opposite over adjacent. So we have the tan of the angle, which is labeled A in this case, equals the opposite side, which is 8, over the adjacent side, which is 11. And so when we simplify that fraction down to a decimal, we do 8 divided by 11, and we get 0.7273 when we round it. And so now what you can do is you can pull out that table, go through that tan column, and find one of the columns that has the closest number to that. And so 7265 right here, where am I? Right there, looks pretty close. So I would say 36 degrees. And when there's a case where it's pretty close to two numbers, you're able to be flexible on this using the table. When we do need precise measurements, then we would need a calculator, but in most cases the nearest degree is going to be accurate enough for us. So that's all there is to it. When you're finding a side, you take your two sides that you have, make sure you label them properly as opposite and adjacent, divide them, and then take that ratio there as a decimal and find the matching angle. To find C, you could then change this where we would make C our working angle, this would become the adjacent, this would be the opposite, and do the same thing. But it's a triangle. We have a 90 degree, we have a 36 degree, so C is just 180 minus 90 minus 36. And you can do that instead of doing the full calculation. Unless you're explicitly told to do the calculation using the ratios, then you can just do that and quickly get the answer. In the case of finding, and so this is the same if you have the sine ratio or you use the cosine ratio, you just have the hypotenuse and then one of the matching sides, opposite or adjacent, and then you just pick sine or cosine, but the process of actually calculation is the same. The difference comes when you're calculating for missing sides. So if we do something like 6a quickly here, 6a had, let me scroll down, the angle given at 58, and then we have an opposite side of x and an adjacent side of 4.2. So we're trying to find x to the nearest tenth. And so what we'll do is just draw a quick little sketch of that. And again, it's usually a good idea to draw a sketch, especially as you're learning this, just to make sure that you can label everything. It doesn't have to be perfect, but we do have our opposite side here. We have our adjacent side here. So again, this is tan, and this whole section is tan at first. But we use the tan of the angle, which is 58 degrees, equals the opposite side over the adjacent side of 4.2. And so there's our little setup. What we can do now is either do tan 58 in your calculator if you're in degree mode, or go to the angle 58 on our table, and we get 1.6003. And now, to solve for x, we just move that 4.2 over and multiply it by the 1.6003. That'll give us our x. And when we do that, I'm getting 6.7. So that's all there is to solving the angle for a side if you're given the angle as well. They're really small, simple calculations. It's just a matter of picking which one you want to use. Do you have a situation where you have sine, cosine, or tangent? And labeling that triangle and picking that formula going to be your key concepts there. So if we jump ahead now, in the case of the word problems here, there was 9 and 10, just to quickly discuss them. In 9, you're just given the triangle already, and so now you're just finding the width of the river. So it's an example of what you could use this for, but you're just using that same idea, solving for that opposite side like we just did, given that triangle. In the case of 10, in this case you're solving for the adjacent side of that triangle, as that is the missing side there. Otherwise done the same as the previous question. But if we look now at the next section, which is 7.4, and we're looking at sine and cosine. Again, the sine ratio, the cosine ratio actual calculations are done exactly the same as the tangent ones. So I want to focus more on some of the word problems with these now, because then we can look at the application of that. So if we look at a question, what did I mark off here? Number 10. Number 10. Yeah, so number 10 is just standard word problems start at 15. There we go. So look at 15. So question number 15 here. Dimitri has let out 40 meters of his kite string, which makes an angle of 72 degrees with the horizontal ground, which is illustrated there. Find the height of the kite to the nearest meter. And so in some of these questions, they've fully completed the diagram. Some they haven't given a diagram. Some they've given a diagram but only given some of the information in it. But they did already tell you that the kite string he's let out is 40 meters. So this line here is 40 meters. So I can switch over here to my notes and we can do that question. So we have this triangle here. That 40 meters is going to be on the hypotenuse, and he had an angle of 72 degrees here. So we want to find the height of the kite, so that h over there, we want to find that height. So in this case, we have the opposite side, and we're given the hypotenuse. So we need to find the opposite. We're given the hypotenuse. So we can use the sine ratio to do that. So sine 72 degrees equals the opposite, which is our h, over hypotenuse of 40. And again, we just pull out our sheet or type in sine 72 in our calculator that's in degree mode, and we get 0.9511 equals h over 40. And then again, just multiply 0.9511 by 40, and that should give you your angle, or sorry, your side length, your height of the kite. In the case of part B, suppose the sun is shining directly above the kite. How far is the kite shadow from Dimitri to the nearest meter? So what it's saying is that if the sun was shining straight down here on Dimitri, what's this adjacent side length? So you can use the cosine ratio there. You could use tan and use the value you just found, the height, and so you can use opposite and adjacent. But whenever you have a chance to use the original value, so there's cases, especially when you get to sine and cosine, where you'll have to use the new value you calculated. But if you made a mistake here, you'd also make a mistake here then. So go back, use that hypotenuse, use the adjacent side. Cosine 72 equals our x here over 40, and solve that. Number 16 was another question I wanted to just mention here. So during takeoff, a plane must rise at least 20 meters during its first 1.5 kilometers of flight to successfully clear the runway. So we want to know the minimum angle in this case of the plane to safely take off to the nearest hundredth of a degree. Again, if you're not using the calculator and you're using the sheet, I'll take to the nearest degree in that case. And if I was giving an assignment, generally I'd use the sheet versus the calculator. But if we were to calculate that, you do have to be careful because this is 20 meters, and this is 1.5 kilometers over here. So you have different units, and that can be significant if you just use 1.5 and 20 as your values versus 1,520. And that's why they give to the nearest tenth, because we should get a small decimal here. And so you'd actually have, in this case, tan theta is equal to the 20 over 1,500. So that's the actual ratio that you would have there. So 20 divided by 1,500 is going to give 0.13333333333 repeating. So on the table, what you would get is 1 would be the closest to that, I would say. So theta equals 1 degree, or if you used your calculator and went to the nearest tenth of a degree, what you're going to do is when you're going to press second function or shift or whatever, you should get a tan to the -1 sign there, and then you can put in that answer of 0.013333, and so you'd get about 0.76 degrees, so about 0.8 degrees as the actual value to the nearest tenth. So we're pretty close with the 1. But the next part is really where I want to look at that question. So it says, if the required rise is doubled to 40 meters, does this double the climb angle? And so if we're going instead from 20 to 40, then when we do that, we again have that same kind of setup. So instead of 20 here, we have 40, and if we actually calculate that out, we're going to get 0.0266, and the angle itself becomes 1.52, and just I want to check something here. I want to make sure I get the right, the same angle we had before to multiple decimals in this case. So it does approximately double the angle in that case when we double the height. And why would it double the angle? Just so I was going to show you the calculation, but I hit clear on my calculator a couple times. But if we double the size of the angle, you should be doubling, or you're doubling the height on that angle. Sorry. So you're taking that angle that was here, say, and you're doubling it. So you should see relatively a double in the angle. Now that is not 100% true because it's not an exact doubling, but it's an approximate doubling. But as you increase that height, that you'll end up getting some diminishing returns on that to some degree. As you continue to double that, the increase in distance won't be exactly double each time. Just a bit of a thinking question. Anyways, off on a bit of a tangent, and which is actually related to the term tangent when you get to drawing circles, which we'll find out later. These are actually all related to circles. Strangely, triangles and all the sine law, cosine, or sine, cosine, tangent, and all that are all related to circles. Now, it's one of the, depending on how the teacher starts it, generally I start grade 11 with that concept. In the case of the last question, then there was question number 17. Just a quick look at that here. 17. When you're drawing that triangle, you know you got a right triangle because you have angle Q equal to 90 degrees. So just draw a right triangle and then label angle Q as 90. P and R do not matter in that case, other than you need to ensure that angle R would be labeled as 41, and then the side PR, which would be the hypotenuse in this case, would be labeled 20. So just be careful when you're drawing it. Start with your right angle when you're given a right angle triangle. If you're not given a right angle triangle, then it doesn't matter, and as long as your sides are labeled right, it doesn't matter if your diagram is accurate or not. Okay, so just a couple more questions to take a look at here that I think have some value to them. And I think number 1 and 7.5, so we're going to jump ahead here to 7.5. The number 1, 2, 3 sequence, I think, is a kind of useful question and has some useful concepts to look at. Covers a few different things. So the first part of that question then is a telephone pole is secured at the top of a guy, and a telephone pole is secured at its top with a guy wire as shown. So there's one of those wires that we use to help support that pole, keep it upright. The guy wire makes an angle of 70 degrees with the ground and is secured 5.6 meters from the bottom of the pole. Find the height of the telephone pole. So this here, just a simple tangent ratio type question. We're looking for the opposite side. We have the adjacent. We have an angle. So in this case here, we're just going to set up a quick tangent ratio, and we have, again, the, what was it, 5.6, 70, that's our right angle, and then there's our missing height. So we'd have tan 70 equals x over 5.6, the opposite over the adjacent. Getting a little sloppy here. And then we'd calculate our tan 70, and we're going to get 2.7475. And then again, we're multiplying the opposite side there, 2.7475 by 5.6 to move it over. And when we do that, 2.7475 times 5.6 is 15.386. So that's our x value. And so we could use that as our height, saying about 15.4 meters up in the air. So now, if we look at part 2 of that, it had just asked to find the length of the guy wire. So that's the hypotenuse. And so if we do part 2, then all we're doing is finding the length of the hypotenuse. So we got the adjacent, we got the hypotenuse. Adjacent and hypotenuse are the cosine ratio. So cosine 70 equals the adjacent, which is the 5.6, over the hypotenuse. So again, our cos 70 can be found using the table. 0.3420. 3420 equals 5.6 over x. And then again, whenever you have an x on the bottom, the easy way to do it, you're going to end up moving the x up, and then you'll move this down. So I just switch the two in one step. We get 5.6 divided by 0.3420. And that gives us an x, or a guy wire length of 16.37. So there's our guy wire length. And now it said in part B here, use a different method to find the length of the guy wire in question 1. So it wants us to use a different method. So here we use the cosine law to do that. Well, because from question 1 we have the height of the triangle and so we have the height of the triangle, and we have this. We could use as another method Pythagorean Theorem. So don't forget, you could, if you have two sides and you're finding the third side, Pythagorean Theorem still works. So you could fill that in. 15.4 squared times itself plus 5.6 squared times itself will equal the square of the hypotenuse. So when you square root that, you should get about 16.37, just depending on rounding. Now, part 3 of this question, it is a little bit longer written. Referring to question 1, a second guy wire is added to support the pole. It is to be secured to the ground twice as far from the pole as the first wire on the same side as the pole, attached at the top. Draw a diagram to illustrate this. So if we draw a diagram and then find the length of the second wire and find the angle formed between the top two wires on the pole. So you would have what we originally had there. So there's our pole and our guy wire. And this was 70 degrees. And this was 5.6. And then the guy wire in this case was going to be twice as far from the pole as the first wire. So we're going to head out here with it. And now we just have this big triangle here we're working with. And it's going to be another 5.6 from there. So there to there, 5.6, or in this case 11.2. So you would calculate the you have this whole side, and you have this side already. We already calculated this in part 1, right? This was 15.4. So in this big triangle, and if we redraw that big triangle really quick, so this is the big triangle. It's 11.2 and 15.4. You can find this angle up here. So say that's angle theta. And then you can find this angle. We'll call this beta. Beta you can find by just doing 180 minus 90 minus 70. So beta is only going to be 20 there. So that's going to end up being 20 degrees. And then to find this angle, it's or the distance, the difference in angles. It's just find that angle using tan, and then subtract the 20. So that's how you would kind of approach that question. And then what else did I have here? A couple more question marked off. I had 13, 14, and 21 I wanted to discuss. So if we take a look at 13, 14, and 21 really quickly. Where are we here? 13. Okay, so 13, this is one that comes up more and more as you move forward in some of your courses. So I just wanted to get the diagram set up for you guys with you. So you got a scuba diver that swam north 1.5 meters per second across a current from east to west that was moving at 2.0 meters per second. She swam for 3 minutes and then surfaced. So we want to draw a diagram showing where the dive boat will pick her up relative to where she dove, and then figure out how far she traveled. So looking at this one, when you're setting up diagrams like this with distance, I like to first get an idea of where I'm going. So I'm going north, and then the current's going from east to west. So if I set up a little compass point here, north, south, east, west, we're going from east to west with that current, and she is swimming north, so she's going this direction. So I have these two directions, so my triangle is going to look like that. If I make that a little bit bigger, maybe you can see it. So it's going from east to west. There's north, there's south. So she's going north, the current's flowing that way. So these are the two pieces that we have in there, and she's getting pushed along that path idea. So this is this kind of setup. Now, what I would do is take these as distance vectors. So let's kind of model out what's happening is that as she's swimming, so she was trying to go north, No, this is maybe in red here. She was trying to go north, but as she was going north, she was getting pushed towards the west by the current. So she ends up traveling this way, and so we just flip that triangle, and there is a right angle. So those are two angles we're working with, and this here would be perpendicular, or sorry, perpendicular to the direction. So this is the actual triangle that we want to look for. She went north, and then she got pushed in that direction. And those triangles will have the same angle set up in them, but what we can do now is actually diagram this out properly. So we have the north travel, and then the vector for these are called, and they're called vectors when there's a direction and a speed related to them, and a measurement with them. You'll get to that in grade 12 math. But there's our diagram, and then our actual distances. So she was traveling for 3 minutes at 1.5 meters per second. So 3 minutes is 3 times 60 seconds, or 180 seconds. And then we're going to multiply that by the 1.5, and that's going to give us a 270 meter distance that she's traveled in the north direction. And then the push of the current would have pushed at a rate of 2 meters per second. So again, we have that 180 seconds times 2 meters per second is 360 meters. So that would be your actual setup for that question. This is Peggy, was it Peggy? No, it's just scuba diver. I'm looking at the wrong question. It was just the scuba diver. So the scuba diver was traveling here, going north, and if there was no current, would have just went straight 270 meters. However, because the current was pushing at a rate where it pushed 360 meters that way, that is the result here. So she ends up over here from that initial position. And then you can use the Pythagorean Theorem in that question to find the hypotenuse, which is the part B, and then you can calculate any angles using sine and cosine. It doesn't actually ask you to solve it for angles, though, so you're just using Pythagorean Theorem in that one. And then number 15, if we switch over to that one, number 15, was it 15? 14, sorry, 14. 14, the observation deck at Peggy's Cove Lighthouse in Nova Scotia is about 20 meters above sea level. Actually, I'm looking at a picture of that on my wall right now. Was there. Cool place to go if you ever get a chance. But anyways, it's about 20 meters above sea level. From the observation deck, the angle of depression to the boat on the water is 6 degrees. So when you're drawing this diagram, what you want to do is, so you got your lighthouse here. It kind of looks something like this. It's kind of like that. And then you have an observation deck up here. And then what you're doing is you have a height of about 20 meters. So that's the height of that portion. And then the angle of depression of a boat on the water. So you got a boat over here on the water. The angle of depression is based off of looking, if you were looking straight out and then you look down at the boat, that's the depression. That is what is 6 degrees. And then you can use that to find the boat from the lighthouse distance, and you can drop a line down here. So that line would be the height of the tower above sea level. So there's your 20, and you want to find the distance from the boat to the tower or lighthouse. So that would be the setup for that one. And then again, you would use tangent ratio, because again, tangent ratio tends to be the one most commonly used in a lot of questions. Is there any more? 21. 21. Okay, so if we look at 21, just a few pages over. So You have the Coast Guard boat is 18 kilometers east of the a lighthouse, and a disabled yacht is south of the lighthouse. How far are they apart and whatnot? So again, when you're drawing this, make sure you just set yourself up with a little compass kind of setup like we did in 13. And in this case, you don't have to. They're directly that position and distance away, so you don't have to do any calculation to figure out how far the lengths are. But that is your basic setup there for that one. And that, I believe, covers all the kind of key concepts out of there. Again, if you have questions at any time, feel free to send me a message via email or Edsby. I can answer those. Next week, we'll take a look at the sine and cosine laws, and that'll be the last major concepts, other than looking at some of the problems afterwards. Okay, you guys have a good week.